So good morning. Welcome to Krishna's classroom. So we continue with the proof of implicit function theorem. Last time we looked at an example and investigated in some detail how one could prove this theorem. So this is a continuation from that. Now we go to the actual proof of the theorem in the general scenario. So let us just recall what all things we state in the theorem so that we can prove them one by one. Or I'll put the statement of the theorem. So we have an f from E to R. E is a E is an open subset of Rn plus M. And then of course we have the following. We take AB belonging to E and such that f of AB equal to 0. For some AB belonging to E. Now we define A to be f derivative at AB, which you know is a linear transformation from R. Then of course it has two parts, one corresponding to, so we have A HK, HK belonging to, so this is written as AX H plus AY K. See here H belongs to Rn, K belongs to Rn. That's a breakup that you have. And AX in fact is a linear transformation from Rn to Rn. Okay, so you can talk about its inverse if it exists. And we have HK is actually equal to H0 plus 0K, and this I write as H plus K. That is the breakup that you have. So AX is from Rn to Rn, AY is from Rn to Rn. So AX they are linear transformations. So this belongs to LRn and AY belongs to R. That's the breakup that you have. So I'll write AX. Now what the theorem says is the following. Now we assume the following. Assume is invertible. This is one assumption that you have. Invertible. That's one assumption that you make. Then the first statement that we are trying to prove is the following. There exists in fact U is contained in E. Okay, so let us take and Rm with U and B belonging to W such that for every Y belonging to W there exists a unique X belonging to Rn with the property that and f of equal to 0. Okay, so this is the first statement that we want to make. So what we want to say is that, show is that there exists an open set U in E and W in Rm with AB in U and B belonging to W such that for every Y belonging to W there exists a unique X in Rn with the property that xy belongs to U and fxy equal to 0. So we first prove that this statement, and then after we finish the proof of that, then we go to the other parts of the statements. Okay, so this is our objective is to write a proof of this part. Okay, so what we want is, we are looking for a U to W. So U we have to somehow is a part of Rn plus M. Now what we do is, as I have demonstrated last time, see, you construct a new function which is, from using the function, the given function f, such that it is from Rn plus M to Rn plus M, and then we restrict that the range to Rm, and then from there we get hold of the particular W. So let us explore this. So what we do is, one, that is this part. Okay, so define Rn plus M by f of equal to, we bring in the given function here so that this is a part of Rn and then 1. So this is now in R. Okay, this is in Rn and this is in Rn. So it is in Rn plus n. And xy is picked in Rn plus n. Okay, right. Now what we assert is that under this particular assumption, that is Ax is invertible, okay, we can prove that f derivative is invertible. Invertible. That's the assumption that we make use of. Okay, so let us compute this. So our job is to compute this. Now we know that, so f of AB equal to 0. That implies capital F of AB equal to, so the image of AB under capital F is 0B. Okay. Now we use the following fact, namely, so let us compute this f derivative. Okay. So you see that f of A plus H B plus K, where H belongs to Rn, K belongs to Rm, minus FB, FAB, which is 0. This is equal to, because it is differentiable and we have already this f dash AB equal to A, this is A acting over the vector HK plus R of HK. So this is the remainder. This is actually A acting over HK. R HK is a function of H and K, not necessarily linear, whereas this is a linear function. Okay, right, where A is equal to f derivative of AB. That is the given. Now let us compute now the derivative of capital F. So we keep this in mind and we write down f derivative of AB. Let us compute this. Now this is equal to, so what do? We look at this f of AB minus, sorry, f of A plus H B plus K minus I think I wrote the right. So what we do is, we shall compute AB. Now to compute this, what we do is, we work with capital F. So from the definition of derivative, we work this out. F of this is equal to f of a plus h b plus k and f of ab is 0. Okay, therefore what do you get? This is equal to f of a plus h okay minus, this is vector difference, minus ab comma b plus k minus b is k. Therefore this I can rewrite as a acting over hk comma k. This I can rewrite as a hk k plus now as h and k go to 0, this goes to 0, this also go to 0. Okay, so if you divide by this, so you get derivative. If you can write this in this form ahk. So a is from using a you can write down the derivatives. Therefore you see that the derivative turns out to be simply this one. Sorry, this is 0. Right. Okay. Therefore, what is this? This is equal to ax h plus ay k k 0. That's right. Therefore, what you have is this. See, it maps f dash hk will be essentially this. It maps hk to axh ayk comma k. Okay. So what you have is this. That is f dash ab of hk equal to any vector is mapped by the invertible operator to 0, then that vector has to be 0. Okay, so let us prove this. So what we want to prove is the following. So let me take out this. This is mostly computational. So I am not going to take out the statement of the theorem here, but I will just keep this part. So the question is now you know that f dash AB is invertible if and only if equal to 0. So this is the one that we are trying to prove. So we have already computed what f dash AB is. Okay. So we'll look at this. Equal to 0. What is it we have? Implies, what is it? You have A HK that is 0 0. What? Don't have any confusion. Okay. That of course implies K equal to 0. Okay. Which implies A equal to 0, which implies equal to 0, but which implies hence so we have proved that is f prime of AB HK equal to 0. One way it is simple is if and only if therefore this is what we wanted to prove. That's the first thing that we wanted to prove. Okay. Now what is the implication of this? Now look at f dash AB is equal to 0. What does it tell you about the function fxy? Okay. So this is f dash AB is 1 to 1. Therefore, by inverse function theorem, there exists open sets U, V contained in where of course U is contained in E. In fact, it is more precisely so. Such that AB belongs to V and F is a bijection from U to V. So that is about the existence of U and V. Now you note that V is a part of what I do is I take the intersection of V with Rm. So let W be defined as the set of all Y belonging to Rm such that and this is essentially the intersection of, okay, this is equal to V intersection okay, whereas Rm is considered as a subset of, so V is contained in So that is W. So it's something like this. You have got V. See, you have got V here, and Rm is here. You're taking the intersection of this. This is your W. Okay. So that's the definition of W. Now, one thing that you can observe is that as a part of Rm, W is open. That's something that you can immediately observe. Now you see that W is that is because you look at V is open in Rn plus M, and Rm is not open in Rn plus M. Okay, so you are taking the intersection of that with Rm, and Rm is open in Rm itself, and this intersection is a subset of Rm. Therefore, you see that this is open in Rm. Now suppose you take, if Y is an element of W, then belongs to what? V contained in Rn plus M. And what you have is that 0y, this is equal to f of xy for some xy belonging to in fact more precisely you can say that for some xy belonging to what you okay. What does this mean? What does this mean? Okay, why is it so? See, this is an element of V. 0y is an element of V, and F is one-to-one map from U on to V. Therefore, for each element in V, there corresponds a element in U. And so that we write as f of xy. In fact, there is a unique choice that you have. Okay. That is, what is the meaning of this? What is f of xy? So f of xy and this is now equal to 0y equal to 0. That means for such a y, that is for any y belonging to W, there exists an x such that in fact this x belongs to Rn. Such that equal to 0. So we have proved the existence of, this is the important part, that is there exists. So that is the existence part. That is the existence part. Now what we assert is that the choice is also unique. So let us prove next the uniqueness. Okay. Now what we want to assert is this. So let us start with the y belonging to W. We know that there exists x comma y belonging to U such that f of suppose x prime such belonging to equal to 0. Then what do you have? Then we have f of and this is 0. So you have f of both xy but since f is 1 to 1, f therefore you see that x prime y equal to x y. So there is a unique x such that these properties are, the required properties are satisfied. Okay. Let me not now still, so we have more or less proved the theorem, the first statement of the theorem. Now let me write down the second statement now. Okay. So having got this, what is that you are asserting? Second statement of the theorem, or second part of the theorem. So what is the consequence? The consequence of this is that given y belonging to W, there exists a uniquely determined x in U such that, so given where exists a unique x belonging to Rn such that xy belongs to U and f of 0. This is what we have proved. This implies we can define a function from W to Rn such that that is actually G is from W to this class. Such that x is equal to 0. So you are linking up this y with this x, and which implies f of gy equal to 0, y belonging to This is what you have. Now what we want to prove, there are some inferences that we want to make. Because here we are assuming F belongs to C1. It's a C1 map. Now you see that the consequence of this is that G is also a C1 map. So that you can talk about G derivative. G is a C1 map such that GB equal to A and GY so how do we assert this? We have seen that we have defined where X belongs to now you see that we have and F of this is equal to F of GY this comes from Fxy equal to 0, X is equal to GY. Then what you have is this equal to F of GYY, which is equal to 0y. Okay. So you have f is 1 to 1 and on to. So f is a map from, let me write, it is 1 to 1. So what do you have? So since f is a 1 to 1 map from u to v, therefore f has an inverse. Let us define this. So what does it say? So that is G is a map from V on to U which implies, since F is a C1 map, okay, this follows from, since F is a C1 map, as a consequence of small f is C1. F is a C1 map. Okay. Now, what about F is a, okay, G is a C1 map. Okay. So let us write down what G is. Okay. Right. So we claim G is so what about G? G is acting over 0y. G of 0y is equal to Gy y. The reason is f of Gy y that's the reason. Okay, so f of now let us compute C1 map from W to U. So that statement we have proved. Okay, so we have proved that this is a C1 map on this. So let us now complete the next part of the statement. So let me write down the next part of the statement. Okay, so the next part of the statement is that so we also have that GB now we compute. So what we want to prove is this, that we want to prove that, so we have GY equal to 0 for every Y belonging to W. That we have proved, and G belongs to C1. Now we prove that G derivative at B is equal to minus AX inverse A1. Okay, so G dash B is from where to where. Now you see that W is a part of Rn, and G is a map from, so GY, therefore what we call the G dash at B belongs to R. First check whether this is true. You see that AX belongs to LRn, that is, it's a linear map on Rn and invertible. Therefore, AX inverse belongs to. Now, what about AY? AY belongs to, it works on okay. Therefore, what happens? AY carries a vector from Rm to Rn, and then AX inverse maps it from Rn to Rn. Therefore, what happens is the cumulative effect of this is that it is from Rm to Rn. Okay, so that is what I have obtained. So it is quite a feasible statement. Let us prove that this is so. That would in turn complete the proof of the theorem. Okay, so what we have is, so let us define the following. So this is phi is of course a map from Rm to, in fact it is from W to, which is a part of Rm, but it goes to U. U is a part of Rn plus M. Okay, so let us therefore what you have is this, that is f of which you know is 0 W. This is actually f of xy, where x is equal to gy and f of xy is equal to 0, therefore this is true. Now we differentiate using chain rule. We have f derivative at phi y, phi derivative at y, this is equal to 0. Because f of phi y equal to 0, we are taking f composition phi, taking its derivative. This is equal to 0. So f of phi b this is equal to, which is equal to 0. Now f derivative of this is equal to a at y equal to b, because this is essentially was at y equal to b, f phi y ab, which is equal to 0. So f derivative at ab is the derivative of this one, and which we have computed, and this is equal to a, right? Which implies a of equal to 0. That is, we are using this relation. Okay. Now we will write it up in detail. So this is equal to a of GB this is equal to ax of which is equal to 0. This is true for every k Rm. Now that implies Ax or this is equal to is the zero operator, which implies since Ax is invertible, so that completes the proof of the theorem. Okay. Now we can write down the last relation can be written in the component form. So we make a remark. I think I have proved the theorem totally, and then now we make a few remarks and we go back to our example. Just make some observations. So we write this last relation in the component form. So in the component form, equal to 0 is, of course, we'll put it this way. So let me write. Minus AB for 1 less than or equal to I n and 1 or in the partial derivative notation, that is so you just write down, it's quite easy to dgi This is enough. Now for each k, this gives a system of linear equations see, these are given functions, fi's are given functions. So what we are looking for is gi and their derivatives dgi So that is what it is all about. Now let me just go back to our example and connect all this. So we go back to our diagram, which we have used very extensively, and then we are again going back to that, trying to work out this main content of the theorem. So what was the problem that we have looked at? Consider this problem. Equal to 0. And we wanted to write y as a function of and if you have proceeded through the problem, so this is we write as -1. That's it. Now you see that our f of xy, this is equal to so we have looked at f is a map from R2 to R2. So you have I write u as so what is this map? This map gives you the following: -1 0 this is the region into which the mapping takes place. So this is the range of Now what we have is this part. Now this is our W. Okay, W is not this. Now this is the line, the vertical line, which is the image of, you see, yeah. This is u equal to 0. That means the circle that we have, this is the circle, and this circle gets mapped to this. This is the image of the circle. Okay, and you can specifically see that the trouble that you have is at these points. In fact, this whole line maps to this and this one. This is the image of the y-axis. So this point is the image of this. 0, 0 goes over here. So this line bends into and moves up and bends into two parts like this. Now what you have, suppose you have an AB here. Then you have a U here. And then there is a corresponding point here. This is 0B. There is a V here. That's about F maps U onto V. And what you have is this part of the line. This is what you call the W. Okay, right? This is the map that you get. Therefore, this is the image of the y-axis. Okay, so this is your W. This is the W portion, this interval, and there is the corresponding interval here, and this is the corresponding interval. So this is the image of W. Okay, so from corresponding to each y is mapped onto an x, or this is B, this is B, this is A, and you have y getting mapped to an x here. This is the image. Okay, so the function is defined as a function of y. X is defined as a function of y and given by this particular arc. So this is the what is called the implicit function theorem, and you have correspondingly f of this is the implicit function theorem. It's slightly complicated though, but I think it is. I try to resolve it to the extent possible with the geometry. So you see that corresponding to each y here, there is a x determined by this arc or the curve x square plus y square minus 1 equal to 0. It is a generalization of this. In fact, the W becomes essentially the intersection of V with Rn. That is the direct generalization. Here it's the intersection of V with R. Okay? Right? Okay? So that's it. Okay, thank you very much. So let me stop here. So I'll come up with some more remarks on this in my next lecture and conclude the implicit function theorem.